Hello, my name is Azam and I'm a PhD student in the Mechanical Engineering Department at Georgia Tech. I'm also part of Center for Compact and Efficient Fluid Power. I'm really excited to get this opportunity to speak to all you young aspiring engineering students or students which are considering engineering as a profession. Mainly because I'm so much excited to be in this field and solve these amazing, exciting problems. So let me tell you some good things that we do as a part of this research center. One of the problems that we are trying to solve is increasing the efficiency of the fluid power systems. As you may know, in today's world, you come across a lot of hydraulic power systems, right from aerospace industry where you have plane actuators for the wings, landing gears for the planes, robotic actuators, excavators, and whatnot. Everywhere you find these hydraulic actuators, and it's a critical component of this designing of the systems to make sure that they perform very effectively, efficiently, and give you the best performance. To do that, we need to make sure that the fluid that is the operating fluid of these systems does not leak out of the system. And we also need to make sure that the frictional forces that are considered losses of the system are minimized so that we achieve the best performance out of the system. Now let me tell you how we do that, how we go about finding such solutions to these problems. We typically do what is called as multiphysics modeling. What is this multiphysics modeling? It may sound a little complicated. It's not. It's really not. It's just understanding what is lying in the system, what physics governs the system, and it's so beautiful thing to understand each and every physical aspects of the behavior of the system. For example, we study how the fluids behave, which we call fluid mechanics. We study how solids behave, we call solid mechanics. We study what is the effect of heat transfer and different temperatures on the behavior of the system, which we call thermal transport. We study what are the effect of vibrations of the system on the effectiveness of your project. We call it vibration analysis. And there is also something interesting called some of the materials that are used in these seals are memory. They have their own memory. Isn't it like cool that these materials can remember what has happened to them in the past, and they decide how they are going to behave in the future depending on what has happened to them in the past. So it's cool that you can model or you can analyze the memory effects of these materials, which is called viscoelasticity. So we try to take all these different physical phenomena together, and they couple them into one solid framework, and we call it multiphysics modeling. And all these phenomena are governed by mathematical equations, and it's beautiful that one equation called differential equation for each of these phenomena can give you a path to the future. You can really predict the future using these mathematical equations. This is such a wonderful thing. So what we do is we form these models which consist of these mathematical equations, and we need to solve them very efficiently. And to do that, we need to solve them on the computers. Now, to make sure that our computers understand what those equations mean, we need to convert these equations into special forms. We call it as finite element analysis, finite volume methods, which are all just different things, different methods utilized to make your computer understand how you want to solve these problems. So once we do that, then we solve these equations simultaneously, and we get a beautiful solution to the system, and it gives us nice future behavior of the system. Let me tell you one typical day of my life as a graduate student. What we do is we need certain parameters for our mathematical models, and to do that we need to do certain experiments. What we do is we take certain samples of the seal materials that are used in the industry, and we observe them under very powerful microscopes or other optical instruments. And very smooth looking surfaces look like Grand Canyons under those microscopes. It's like a lot of mountains and valleys, and we get some certain parameters from those experiments, and we put them in the model, and we solve our model. So that's what my typical day looks, and then once we get those models, we write computer algorithms to solve these problems efficiently. I've been asked to give you some advice. I don't know exactly what advice can I give, but one thing I would like to say is that if you do decide to study engineering, don't do that just for the sake of living a better life or earning good amount of money, because those things will follow. But what you have to understand is, if you have to, there is so much to offer by this nature, and if you really take a good interest in understanding fundamental mathematics and physics, this nature will unveil its secrets to you, and it's such a wonderful joy to know these things, that how these things behave, how things operate, and just do that, and you will find very beautiful things in nature. Thank you very much.